Good afternoon, everyone. It's my pleasure to come to Paris and give a presentation about our research. And I'm very happy to get acceptance of this paper and would like to introduce a novel application of optimal transport in seismic imaging or in geophysics. This is a joint work with my PhD advisor, Björn Quist, and many other people. Like my previous colleagues in UT Austin. So first, I would like to introduce the background of this application. So in seismic imaging or in explorational geophysics, what people are interested in is where is oil and gas. But we cannot dig a hole and to find it where it is. So before they drill, they first do this kind of seismic thing. So there's a truck, or it's a truck here on the land measurement, but if it's on the sea, it will be marine measurement. There will be a ship. So this truck is going to send signals down to the earth, and because different properties, sand, rock, oil, gas, they have different velocity density. So the signal back propagated to the surface will have different properties. So we have sensors and receivers all everywhere on the surface and measure this real data. And the geophysicists, they analyze this kind of data to determine what's going on under the ground. So that's a big sighting of seismic inversion. So what we get from the receivers is signals like that. So it's waveforms. This line is time, and this line is the receiver, so it's space, and this is time. So they look like this. And what we are doing is to analyze these signals to see what's going on under the ground. And this is one benchmark. Actually, the marine acquisition, this is what's going on under the sea. So here is salt, here's salt. Part of them are sand, something else. So this is what we want to invert for. So actually, this is PDE constraint optimization. The PDE here is a wave equation. And here is a framework of this inverse problem. So as a typical inverse problem, we have our initial guess, which is starting velocity model. And because our guess is not that accurate, when we do one forward modeling, which is PDE, we solve the PDE, we generate our numerical simulated data. We compare with the real data we measure from the receivers, then there's a difference. And based on this difference, which is also residue, we can use gradient-based update or Hessian-based update, but most of the gradient, since it's too expensive. So we update our velocity model. And again, we do one forward modeling by solving a wave equation and then compare again. So this is one, actually this is better. This is one cycle or one iteration in the seismic inverse problem. So it's constrained by our PDE. And we want to update the velocity or some other parameters in our wave equation. The focus of my research is which one is a meaningful misfit function for this inverse problem or for this optimization problem. Most of the time, people use the least square norm. Like everybody is very familiar with it, is L2 norm. So this is simulated data, and this is the real data. We square the difference and integrate in time and sum over all the receivers. So we treat it as a function of our PDE model parameter M. And we want to minimize this quantity to get this model parameter M. So this is when we use L2 norm. This has been brought up 3 decades ago. It's very classic, but it has a problem. The problem, I think it comes from the oscillatory of these waves. So here is I have 2 recurve wavelets, the blue one and the red one. Because seismic data, they are periodic and they have positive and negative sides. So if I change the red one with the blue one, so it will be a shift. And the shift, it can be 0, can be -4, can be 4. Then I move it from the left-hand side to the right-hand side. And I measure the L2 misfit. Then we get a sensitivity curve like this. When the shift is 0, these 2 coincide, you have misfit 0. But when the shift gets larger, we have local maximum and local minimum because of the oscillatory property, and also it has cycles. So we have so many local minimum, local maximum. And if we optimize with this specific function, we start like -4. It's very easy, you get stuck here and stop in the optimization. So that's the disadvantage of the L2 norm. But for W2, if we compare these two in Wasserstein distance, quadratic Wasserstein distance, we get this global convexity curve. And that's the motivation to, in optimization, use this one instead of the L2 one. And the next is the, okay, it's just a brief introduction of the history from Monge to Kantorowicz to all the recent mathematicians since late 90s. And right now it has been used a lot in imaging, like they call Earth mover distance. And then recently machine learning, they also compare with KL divergence. So here what I'm using is in Sesame imaging to do inverse problem. Okay. And so this idea has been implemented by two groups, or many groups actually, but in two categories. First is to use W2. The other category is used by W1. So there are some people in Grenoble, they have published several papers about it. In their papers, they use KR norm, which is a relaxation of the W1 norm. And in my group, we stick to the W2 case. So here is a normal formal definition for W2, but I think most people already see it a lot in the talk. So properties of W2, especially in this wave equation setting, we have to think about the theoretical why we want to use it. So here is a 1D wave equation, and everybody knows we can get the explicit solution by D'Alembert formulation. So it will be f of t minus x over c. C is our velocity. Then now we can think about if our velocity is wrong, what kind of phenomena we can observe from the surface. So for fixed location, variation in velocity, we will have shifts in this data. If we fix the time, some variation in velocity will give us dilation in the data. Then if there's some amplitude change due to some errors, we will have partial amplitude change. So based on these three phenomena, we prove several theorems about the convexity of W2 in this wave equation setting. So fourth theorem is about W2 as this distance between f and g. It's convex with respect to translation and dilation. So basically it says if f is a translated and dilated version of g, then the distance as a function of translation parameter and the dilation parameter will be convex. And this basically take advantage of the cyclical monotonicity of the Wasserstein distance in general. And the other one is the convexity of local amplitude change. So if my f, part of it is bigger, larger than g, and the other parts are smaller than g, then the difference between f and g actually is convex with respect to this amplitude change, changing parameter alpha. So it's another convexity. And this proof is by the displacement convexity of the Wasserstein distance. So after exploring the properties, we would like to see how to compute it. I think that's the #1 challenge for optimal transport, because it's not very easy to get the optimal map. So when we first started, we were thinking about the Monge-Ampere equation because of the Brenier have this paper in 1990s. So we know the connection between W2 and the Monge-Ampere equation. So if we solve this Monge-Ampere equation and get the solution U, then the optimal map between f and g in W2 sense will be just the gradient of U. So we can explicitly compute the Wasserstein distance. So this is a highly nonlinear PDE because we have a determinant of the Hessian on the left. And on the right-hand side, we also have G on the denominator. Both of them are numerical challenges. And there's a very good approach by Froese and Obermann And also, I think Banamu also collaborated with them for several papers. So what they propose is to use the monotonicity of the numerical scheme to approximate the viscosity solution of this Monge-Ampere equation. And so they have the very good convergence result in theory. And here is what we do by solving Monge-Ampere equation. So in each iteration of this inversion, we solve the Monge-Ampere equation once. And finally, that's the converging result. So all the pictures I show here are velocities. This is the true velocity, and this is our initial guess. So based on this initial guess, we solve one wave equation, then we solve the Monge-Ampere equation, we compare, we get update. So after 100 iterations like that, W2 converges to the left picture, and the L2 converges the right picture. So it has several wrong properties than the correct one. Because of the local minimum, it suffers. And for W2, this is, I think, is also a very good improvement or achievement for Monge-Ampere equation, because it's a very large data. It's like in time is 1,500, and in location it also has 400 around like that. But we put it into the Monge-Ampere equation and solve it. So in the end, it converges very well to the true velocity. And this is another one. It's the BP benchmark true velocity, initial velocity, W2 and L2. So L2 only recovers the upper boundary because it forms the reflectivity. It's not going to dip anything down. After having these results, we were very happy, but we were also unhappy about it's not really beautiful compared to the original true velocity. And also, if solving the wave equation take one time, and solving the Monge-Ampere equation probably take me 3 to 4 of the time. It's still I think it's still ON for the Monge-Ampere solver, but the constant is a bit of concern. And in the industry, computation power is the most important thing. And for them, this seismic inversion, the most expensive part is forward modeling, which is solving the wave equation. Now I compute the misfit more expensive than forward modeling. It's not will be very popular afterwards. Then we turn to this 1D optimal approach. So in 1D, if we compare data in 1D, what I do actually is W2 in time and L2 in space. So I only compare the time data trace by trace, then I sum over all the receivers. So very similar formulation. So basically, it says 3 steps, and this formula has already come several times in today's optimal transport topic. So that's exactly 1D formula. And because it's exact and explicit, we can get it in ON complexity. And the N is the total number of data in my time. So what I do is first I normalize the data to be positive, then I integrate in time, and then I do an anti-function to get the quantile function. So that's basically 3 steps. And this 3 step is very inexpensive, like almost the same speed as computing the L2 norm. There's one thing I would like to give a notice, is the specialty of seismic waves, seismic data. Seismic data are not like pixels and are not like Gaussian distribution. They have both positive part and a negative part. The good thing about it is it has mean zero, sort of, if we don't have zero frequency. But it has positive and negative parts. This is really unnatural in optimal transport setting because it was brought up to transport sand and some other stuff. So this is the number 1 important step, and I think it's very crucial. So I would like to give several more minutes on how to normalize the data. So we tried several stuff before. I didn't mention this. So in our very first paper, what we do is to take positive parts, compare, and take negative part, compare. It works well if we don't use this Adjoint state method to do this large-scale inversion. We can just do line search to get it. But in order to have a Adjoint state method, we want this normalization method to be differentiable. Otherwise, we can combine together with Adjoint state method. So absolute value we cannot use it. And squaring the data, we have local minimum in the amplitude sense. And taking positive part and negative parts is not differentiable function. So we start to look at some other functions. This is the first one that we try, and it's successful. It's very naive. They are negative, so we just add a constant. We add a constant from the blue one to the red one. So after this simple transformation, the data become positive. So we can do optimal transport between this red new data, like the red curves. And since it's a linear transformation, so there isn't really much difference in the gradient part. So, and the second idea was brought up earlier in this year by a researcher in the company. So they take advantage of exponential function. The range of exponential function is always positive. So what he do actually is exponentials of the data f. But exponential function is very dangerous. Its range can be very large. So we have a constant c here to control the value of the final, the data range. So my experience is the maximum c times f, we'd better to make it like 4 or 6. Otherwise, the machine cannot handle this large number, and we will have machine error or blow up. And this is like a combination between this linear function, transformation, and the exponential function. And it's still C1, it's still differentiable. So for the negative parts, I kind of just ignore it by taking an exponential function. So I kind of suppress the negative part of the wave. And for the positive part, I still do a linear transformation, but it's a very small scale. So in total, this transformation function is still continuous differentiable. So it can be combined together with the Adron state method. So it's just a few ideas. It's not limited to this, but that's kind of a way to mitigate the gap between general data to the data that optimal transport theory can deal with. So I would like to do some comparison between L2 and the other related one. So for L2, the difference between two wavelets is like the shaded area. They square the difference in the vertical and integrate in this axis. So that's what L2 do. And if we integrate the data once and compare the L2 difference, you will see still the shaded area, but the shaded area is more smooth. So as a result, it has less the chance to get local minimum than this one. Here is the Wasserstein distance idea. So once we make them positive and then we integrate, so what happened in the past is still recorded in this curve. It's not like general wavelet because it's positive, negative, positive, negative. You cannot see what's happened in the past. And that's why they have cycles, they call cycle skipping, they have local minimum. But once we make it positive and integrate, it's always monotone increasing from 0 to 1. So everything happened in the past is recorded in this shaded area. And what W2 measure is the shaded, the difference in this way, in this x-axis, and we integrate in the y-axis. That's from the 1D formula. And what W1 do is very similar. It's just absolute value in this x difference and integrate in one axis. Yeah, so still 3 steps, very important in this application. Scale to be positive, integrate in time, and do a quantile function. It's not only convexity in the data domain. What we finally want is a convexity in model domain. So here I have a simple example. Our velocity range starts from some certain value and increase in depth with another rate, alpha. So the velocity actually I parameterized to be a function of VP 0 and alpha. So the correct one is 2 and 0.7, but I make my VP and alpha change in some range because I want to see the convexity curve. And finally, I get this 2. So the left one is L2 misfit. By changing the starting velocity and by changing the alpha, I can So what I first do is to do a wave equation. I solve for the waveform, and I compare the difference between this wrong waveform and the reference waveform, and that's what I plot the L2 misfit. So it has a global minimum here, but it also has many local minimum. If you start from some value here, it's very easy to get stuck here by any gradient-based method. And for W2, it's global convex. So it's not only convex in model data domain, in the shift domain, but also in this model velocity domain. So I would like to show some inversion results, but it's not really combined with this one, so I would like to change to the outside. Okay, first is a BP model. So the left is L2, the velocity update from iteration to iteration, and the right is the data residue. So it's the initial data residue, the true one minus the current one. So it's also changing. So after 300 iterations, it kind of only recovers the local, the upper bound without getting to the one up. That's because it creates the reflector, and this gets stuck at local minimum. And also, as you can see, the residue is still there. It's not changing too much. And here is what W2, the Wasserstein distance, do. So the same setting, everything is the same except the misfit function, in the objective function in this inverse problem. So we started to construct the thought body. And after 100 iterations, it's almost there, but in the end, it's trying to do more and more to create more resolution. And in the end, you can see the residue is almost gone. So that's for this BP thought model. And also here is a Marmousi model I would like to show you. So here's the L2 norm. I have 11 sources on the top, and it's very messy as the iteration continues. So many wrong characters, characters here and here, and the residue didn't really decrease too much. And I would like to show the W2 one. So it started to formulate the peak of the correct velocity, and then started to update what's going even deeper. And the residue, as you can see, is almost zero in the end. So another one I would like to show you is the insensitivity to noise of the W2. Actually, it was inspired, we were inspired by a sentence in Villani's book that is very insensitive to noise. So I would like to explain what's here. I have the true data, but I add noise to my true data. So my target data is noisy right now. I add this blue one. And this noise is correlated noise. It's correlated not only in time, but also in the data amplitude. So the one we try to fit right now is this blue one, the noisy one. It's what I want to fit. And the black one is the current iteration data. So as you can see, the data residue is always large. But we are converging to the correct velocity after just in less than 100 iterations. It's very noisy compared to the one that I showed before. But it still converts to the true properties. And for this one, the black one is our current data, and the blue one is noisy data. They are never fit. That's the reason. The question is very interesting, like why we still converge, because these two never fit. I guess the reason is by our eyes and also by L2 norm, these two look very, very different. But if we measure them in W2 sense, they are quite close, and probably it's already converging. And that's why we didn't fit the data, but we converged to the true velocity. This is because W2 is insensitive to the noise, so W2 didn't see the noise we add over there. So I would like to go back to my slides. So that's the first iteration after L2 and W2. You already see the peak. And that's also the first iteration. We already have a look about this salt body. And that's the convergence rate. Very obviously, L2 go to a local minimum, but W2 converge very well in 50 and 100 iterations. And this is the noise I add. As you can see, it's not only correlated in time, but also in the amplitude, in the data amplitude. And that's because W2 cannot see the noise difference, here. So these three curves, one of them is like blue one is clean data comparison. Red one is only one of them has noise. And the black one is both of them has noise. And if I plot the misfit, you can see clearly three different curves in this L2 sense. But if we compare them in W2 sense, they coincide because the noise W2 cannot see. So it's really good in this application. So yeah, I would like to take the time and draw my conclusion. So the motivation of our research is to consider a global misfit, to consider the periods, the cycles, than L2, which is point-by-point comparison. And the good properties we have proved has instituted noise, convexity, and the synthetic models we have this. And also recently, there's a real data example implemented by the company. So what I want to do is, it's still some problems about it, like positive data, negative data. And also the mass balance is a question. So unbalanced transport is also considered over here. So, but in general, the properties of W2 make it a very promising misfit in seismic imaging. Okay, thank you.
Thank you. Are there, yeah?
How sensitive are the results with respect to the normalization, first step after normalization?
Yeah, I think normalization is the most important one. So I only know what already work. So what work is adding a constant and also do exponential, not too big exponential, just normal. Others, I think recently we already know the reason. For example, we square the data, but F squared converge to G squared doesn't mean F converge to G. So this may cause some local minimum. But in general, I think adding a constant or do exponential, especially a mild exponential, will be very effective.
Okay. I had a question concerning the industrial context. This is a quite classical problem. Many people face this kind of problem. So what is used in practice? You told us that, of course, straight L2 estimation is not going to work well. But what do people do? People who don't do what you do, what do they do?
Still, people do a lot of L2, so it has been, it's easy, and especially the gradient looks, it's just F minus G.
Yeah.
So people use it. So how they mitigate it is adding regularization or adding extra parameter dimension. So the question is the data cannot fit the model, so they just add more parameters to hug the data. That's what they say. Add more, for example, we have velocity, but they also add artificial variable over there to fit the data. And there are some, I think that's the main three ideas. One is change the misfit function.
Okay.
And another one is adding regularization. And the third one is adding more parameters to fit the data.
Wow. But does it make sense?
Adding regularization, like we can understand. Changing the misfit, that's what we are working on. So what we want to do is make it as cheap as possible so that people in the field, they can use it. Because in this area, in this field, computation power and memory are number one, number two concern. They don't want to do expensive stuff. And I think the extra parameter, I think, is still an experimental case right now. Yeah.
Okay. Okay, are there further questions? Okay, so thank you again.
Okay.